Hi guys, this is the last recording. Well, it has two parts because YouTube allows me to post 15 minutes at a time. But it's my last recording for you guys. So, a few things before I start with the class today. Not class, the examples, whatever. A few things. So, Dr. Mikolaitis will start on Monday. If you are watching this, it means that you've watched the rest. As you've noticed, most of them have not been long, and I'm doing that on purpose, not just because YouTube allows me to post 15 minutes. Even the ones before were not very long. Why? It's because I understand that it's very difficult what you're going through right now, and I want to keep them short and light and, easy to understand with a lot of examples. So, what I noticed when I checked the other two that I posted on YouTube, there were not a lot of views. So you need to stay on top of things. I know that I passed you all with 50 out of 50, and the university is considering doing SU or pass, no pass for all the classes. But if you get 69 out of 100, so if you get 19 out of 50 with Mikolaitis, you're not going to pass. And with this class, if you don't pay attention, if you are not responsible, it's very easy to get 19 out of 50 or below. Similarly, if you stay on top of things, it's very easy to get very close to 50. I understand that all of us learn the same way, but everything accumulates and it's not a lot at a time. It's just a little bit at a time. So for thermal, like exam number 2 was very symbolic of it, it tends to be hit or miss. Am I staying on top of things? So it's not a lot at a time, and then everything makes sense. I can solve this seemingly complicated cycle. Or am I just, you know, just relaxed, not really paying attention, crossing my fingers? Then very easily you'll get 5 out of 50 with Mikolaitis. He's very fair. All right. And like he said, I'll write you a problem on open systems in your exam. He is, like me, very fair. But he's not going to pass you if you don't do your part. Do you understand this? Even though I'm starting you with 100%. So, just if you are at this point watching this video, it means that you've been watching the rest. In that case, very proud of you, very happy. The other thing is that I don't have like a lot of knowledge on online platforms. Like I have Instagram, I think. Do I? But I barely use it. I do have Facebook because I'm old. So I want to open up a Facebook page, like a group, where it's you guys and me. And then you can ask me questions on thermal because, like I told you guys, Mikolaitis is a very smart guy. So he has big words and you might get confused sometimes. It's fine. I took, well, I'm spending 4 minutes already just doing small talk. I took graduate thermal with him here at UF, and I got an A minus. I got like 90 or 91, which was an A minus. So, how are you taking thermal? How do you trust me? I'm kidding. He's very fair. Granted, I was a single mom of a baby, but he is he knows so much that sometimes we need like an extra push to understand the material. So I'm gonna open that Facebook group, and then it will be up to you to like add other people, and then you can just ask me questions there. What is this? Why am I getting 4 when he got 400? And you can see how that works. All right, so what I'm going to do now, which is going to be 2 videos of 15 minutes, it's a few examples. So there's no new theory on open systems. I already gave you all the equations for steady state, remember, for conservation of energy, steady state and transient, which is non-steady state for conservation of mass, you have the equations, you can handle them, okay? Now I'm just going to see more examples, and they are from old exams. I have this one over here, okay? And I'm going to do this one last, okay? No, I'm not going to do that one last. I have this one over here. I have this one over here. These are all from old exams. And then I have this one over here. So I'm going to be posting them on Canvas, okay? And the solutions, I have them. Solution to the first one. Solution to the second one. Solution to the third one. Looks a little long, okay? These are very good problems. They really help you move forward, okay? So again, these are just examples and no more new material. So the first one, which is this one over here, okay, that is posted on Canvas, it says that you have, or you can look at it, all right? Hopefully you have like a separate, you know, screen, not screen, like separate part of your screen with the notes that I'm going to post. This is that you have a heat exchanger connected to a turbine. So now we have two in series, okay? So all of these, okay, this one, that one, this one have multiple in series, which is what typically happens, okay? Sometimes we have just a pump, for example, or a diffuser to achieve what we want. But in general, for the applications that we will see, and for a lot of engineering applications, we have multiple of them in series, okay? So it's not just one. So what happens when you have multiple of them in series is that you can choose to analyze just one, okay, as your system. You have your boundary around it, and you apply your conservation of energy equation to that one. Or you can pick two. For example, I could pick two, make the boundary around them, and then see what's crossing the boundaries. And you apply my equation to that. Okay, so that's what we're going to practice today. So in this one, it says that we have a heat exchanger and a turbine. So just read it right, okay? It says that you have an amount of water at high temperature entering one side of the heat exchanger. And this water, it says that it's been exposed to certain elements, such as in a power plant, a nuclear plant, sorry, which it could have some radiation, that make it unsuitable for passage through a turbine. So instead of passing the hot water directly through a turbine, you're going to pass it through a heat exchanger, and then that heats up another side, all right, that also has water, and then the other side of water passes through the turbine, okay? Now, that's the assembly that you have over here. So you have the hot water at the top part that, for some reason, you cannot pass it through the turbine, heats up this side. This one now is hot, passes through the turbine, we get power out, okay? Now here we want to find the enthalpy at 3, at 4, T4, T5, power generated by the turbine, if you know all those values over there. So you know M.1, which is mass flow rate at the top, 5 kilograms per second. You know P3, which is equal to P4, 3 megapascals. And you have P5, 75 kilopascals. You have the quality at the exit of the turbine, 0.9. You have that 3 is saturated liquid, and then you have the volumetric flow rate, AV, at 3. So you have all of that. And then there's another question at the end. It says, did the turbine experience heat losses? Do you think the power developed will be greater or less than the value calculated? Well, I'll tell you right now. You have high energy fluid going into it here. So if the turbine has heat losses, okay, then you'll get less power out of it, okay? Some of that energy going into it will be lost. You get less power out of it. Now let's see the solution, okay? We have to find, first it asks us to find just properties. So P3 and H3. Sorry. With P3 and the fact that 3 is saturated liquid, we can find H3. So that's the first thing that I did in the solution, okay? Because we have that 3 is saturated liquid, then it's HF at the pressure. And we find this on A5, okay? Thinking of how long these problems are, this might be 3 videos, okay? Which corresponds to 45 minutes, which is the length of a lecture. So it's fair, okay? Anyway, just examples, so you don't have to watch it. If you feel like, I don't want to watch her, she's weird, or I don't have the time, just read it. It's posted, okay? All right, so HF from A5, you can find it at 3 megapascals. Make sure you know how to do that. You're going to keep doing this the rest of the semester with me, with Nicolaitis, with whoever, okay? So now we found the first one. Great, we got that out of the way. Then we're looking for H4. So then we look at 4. We're like, we have 2 properties there, okay? And I look at the problem statement and I'm like, I have nothing at 4. That sucks, but actually I have P4 because the pressure is constant on each stream of a heat exchanger. And P4 is 3 megapascals. And that's it. And I'm like, I don't have anything. So then I have to figure out if I can find another property somehow, or if I had to use conservation of energy somewhere. Now I know that Q dot going into 3 to 4, okay? Q dot going into 3 to 4 is M dot at 3, H4 minus H3. And that's from when we analyze a heat exchanger with separate streams, right? Or each separate stream. So Q dot, all right, is equal to M dot 3, H4 minus H3. However, what we have given in the problem is Q dot divided by M dot 1, okay? So then Q dot is that value that's given multiplied by M dot 1. That is Q dot, all right? So I can multiply those two and I get Q dot, which is Q coming out of the top stream, Q dot coming into the bottom stream. Now I just have Q dot. And then it looks like Q dot is also M dot 3, H4 minus H3, okay? So that's what I'm going to use to solve for H4. So now I have multiple ways to solve for some of the properties, which can be problematic. Now I look at that equation and I have Q dot, I solve for H3, but I don't have M dot 3. So I look at the problem because it might happen that this is not the way to do it either. And if I look at the problem, I have the volumetric flow rate at 3. So it looks like, you know, that might be useful because M dot is AB divided by specific volume. Now AB is given, specific volume. Can I find it at 3? Yes, because at 3, we have saturated liquid and we have the pressure. So I can find V, and I'm over here now, okay? I can find V the same way that I found H, all right? So from A5, I find specific volume. Make sure you know how to do this, okay? On your own. And I can finally solve for M dot 3, which I manipulated the numbers so you will get 1, okay? And now that I have M dot 3, I go back to my equation that I know from a single stream of a heat exchanger that Q dot is M dot delta H, and I solve for H4. H4, a little bit harder to solve for than H3, okay? Now I need to find T4. It's the next one. The problem says I need to find. So do I have two properties now at 4? Well, let's see. I have H4 and I have P4. I already found H4. So I know that P4 is 3,000 kilopascals. So H, okay, H is greater than Hg if you go to table A5, which means that you have superheated vapor, okay? Because you have superheated vapor, you have to go to table A6. And again, I manipulated the numbers such that you didn't have to interpolate. Mykolaitis sometimes uses a program, like software, for you to find the properties, but he's not going to use it now. I told him, you guys are going to use the tables, all right? Conceptual part, important. Now, I can go to A6 and I can find that. Temperature is 350. Excellent. Just by going to the pressure and the H, okay? Now, the next one is T5. Now 5, it tells you that it's 75 kilopascals and you have a quality, which means that it is saturated mixture. Because it's saturated mixture, T is T-sat. So you go to A5 is 75 kilopascals and the temperature right next to it will be T at 5, okay? And that value is 91.76 degrees Celsius. So not that bad. This is all using the tables, all right? The equations, not a lot so far. Finally, we need to find the power of the turbine. And the power of the turbine is M dot at that bottom stream, which is M dot 3, M dot 4, and M dot 5, multiplied by H4 minus H5, high minus low. H4 we already found. H5 we can find with X at 5, which we have, which is the equation that we use for saturated mixture. HF plus X, Hg minus HF, okay? And we find those values from table A5. And then we solve for H5, and then we substitute and we find the power of the turbine, okay? I'll continue the next one with some comments on this. Thank you.